Yeah, so good morning, everyone. Thank you for allowing me to present here. So my name is Mandip Dahal. I'm a PhD candidate in University of Connecticut. So I'll be talking about studying fiber bond behavior via single fiber pullout test. So just a very brief introduction about UHPC. It's an advanced form of cementitious composite, compressive strength over 120 megapascal, very low water to cement ratio, and superior properties than regular concrete. So a general mixed design of UHPC looks like this. It has a binary material, a type of aggregate, water or any type of chemical admixture, and the steel fibers. But in this work, we'll just be looking at the bond between the UHPC matrix and the steel fibers. Now to study the bond, we use single fiber pullout test where, where we embed the fiber into the UHPC matrix and we try to pull this fiber out and we plot the pull-out load and the displacement of the fiber, which we also call as a slip. So the pull-out load-slip relation can look like this. We can have either slip hardening behavior or a slip softening behavior, and sometimes a constant bond behavior in between. So what we desire to have is a slip hardening behavior because in the tensile test, it translates into a strain hardening behavior. Now in this work, we check for 9 different types of fiber in which we have proposed one arrangement of fiber. But before getting into that, I want to talk about the motivation, like why we studied for broad range of fibers. So the first motivation is the inability of the conventional fibers to engage well with the UHPC matrix. So this is a pull-out test that had been done in 2012, quite a while back. So 3 different fibers were tested, straight, hooked, and twisted fiber. When we look into the fiber stress slip relation, in case of the straight fiber, what we observe is that the fiber stress is quite low. But in case of hooked and the twisted fiber, the fiber stress is very high, but in certain cases, the fiber fails. So among these, sometimes the fiber stress is not high enough and sometimes so high that the fiber is failing. So the conventional fibers are not engaging optimally with the UHPC in terms of fiber pull out in all the cases. Now the second motivation is to find the degree of slip hardening. So we desire to have a slip hardening behavior which can be confirmed visually, but there is no equation to quantify it yet. So we will propose the equation to quantify the degree of slip hardening. Now this is the UHPC mixed proportion we used. This had a 28-day compressive strength of 126 megapascal. We tested the single fiber pull-out test for 9 different types of fiber. We categorized these fibers into 2 different types. One is the bundle fiber and second one is the commercial fibers. These bundle fibers, we prepared this arrangement by ourselves in the lab, and the commercial fiber, we check for 5 different types of commercial fibers. For bundle fiber, we check in 3 different embedment lengths. And for commercial fiber, we check at just a single embedment length, and we compare between bundle and commercial fibers at this embedment length. Now, this is how the fibers look like. This is the properties of the fiber, this is the images of all the fibers, and these are the enlarged images of the bundle fibers. So B2 means 2 fibers are bundled together, B3 means 3 are bundled, B4 has 4 fibers, and B5 has 5 fibers bundled together. So this is the analytical procedure to find out the pull-out parameters. From the experimental data, we get the pull-out load and slip data, and we plug those values here and find out these parameters. For the contact parameter, we looked into the bundle fibers under the microscope, and what we observed is that they had hexagonal packing. So based on this packing, we calculate the contact perimeter and use in these parameters, in these equations. So these are the results for different fibers. For the B2 fiber and B3 fiber, we can see in this slide. So with the increasing embedment length, the load slip curve and the fiber stress slip curve goes high. The shear stress slip curve also is higher, and with increasing number of bundles, the load slip curve and the fiber stress slip curve is also higher. Similar results can be seen in B4 and B5 as well, with increasing embedment, higher curve, and with increasing number of bundles, higher curve. So we take out the maximum value from those curves and we plot the relation between them. So what we see is that in terms of the effect of embedment length, the maximum pull-out load increases when the embedment length goes high, and these are the equations based on the linear regression. Similarly, with the increased embedment length due to increase in the bonding area, the fiber stress is also high. And as the load slip curve is higher, the pull-out energy is also higher, while the average bond strength remains consistent because the increase in pull-out load is balanced by the increase in embedment length. So this remains consistent. Now this is the effect of number of bundles. So what we see is that with the increasing number of bundles, the maximum pull-out load increases, while the fiber stress remains consistent because the pull-out load is offset by the increase in the cross-sectional area or the contact perimeter. Similarly, as the load slip curve is higher, the pullout energy is higher, and the average bond strength also increases due to the improvement in the bond. Now we compare the pull-out load slip relation with the commercial fibers, all at 6.5 millimeter embedment length. So what we see is that the bundle fiber has better load slip relation than other fibers, but in case of the fiber stress and shear stress, except for the twisted fiber, the bundle fiber has the better fiber stress and shear stress slip relation. Now this mechanism can be explained by this figure. So in case of the straight fiber, the only forces that resist the pull-out load is the frictional bond between the fiber and the matrix and the fiber surface pressure exerted by the matrix on the fiber. Whereas in case of the bundle fiber, in addition to those two forces, we also have the mechanical interlocking between the fiber and the matrix and the torsional bond between the fiber and the matrix. And also there is the sequential debonding of bundle fiber, which further adds to the resistance. So the load slip relation of the bundle fiber is higher than that of the other fibers. Now, this is the effect of bundling. We see that if we use multiple individual fibers, the bundle fiber still has the higher load slip relation, and that's due to the effect of bundling due to the mechanism I just explained just before. Similar improvement can be seen in the maximum fiber stress, average bond strength, and the pull-out energy too. Now we propose an equation to determine the degree of slip hardening. So for this load slip relation, first we find out the best fit line for the initial elastic part and also for the slip hardening part. And based on the intersection point between these two lines, we find out the pull-out load and the slip at the debonding point. We also know the maximum pull-out load and the slip at the maximum pull-out load, or the slip capacity. So based on these four parameters, we calculate the degree of slip hardening. So for an actual experimental data, this procedure looks like this. So based on this equation, this is how the degree of slip hardening looks for various types of fibers. So we see the maximum degree of slip hardening for bundle fibers followed by the twisted fiber, and then the remaining of the fibers. So based on this, we can say that bundle fiber has better performance than the other types of fibers. So we also compare our results from the work from the literature, and we do that based on the average bond strength per compressive strength and the slip capacity per embedment length. What we see is that most of the fibers have low bonding strength and low slip capacity. Some have high bonding strength, but they still show low slip capacity. And the ones which have high slip capacity have a low bonding strength. But in case of the bundle fibers, we see a balance between the both bonding strength and the slip capacity. So we can say that these fibers are engaging optimally with the UHPC matrix. So these are the conclusions from this work. So we performed a single fiber pullout test, which is really simple but a very effective way to study the fiber matrix bond. We proposed a bundle fibers which had superior pullout parameters than other types of commercial fibers. We have a new equation to determine the degree of slip hardening, and the bundle fibers have higher degree of slip hardening than other fibers. And we see that the bundle fibers have optimal balance between bond strength and slip capacity than other fibers. So the potential benefit of using these kind of fiber are reduced risks of fiber agglomeration during mixing and casting. So these data are from our paper published in CCC earlier this year. So please feel free to check this out. Yeah, thank you from my side.